Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, I'm really curious to learn what's the connection between health, hot lunches, herd immunity, and hogs. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. And with us tonight is Gail Burrell and Tom Dick. Gail currently serves as an academic specialist in the program for mathematics education at Michigan State University, and she was a secondary teacher in Milwaukee, Wisconsin for over 28 years. She served as president of the National Council of Teachers of Mathematics and the International Association for Statistical Education. Her awards include the Presidential Award for Excellence in Teaching Math, the NCTM Lifetime Achievement Award, the Ross Taylor Glenn Gilbert NCSM Service Award, just to name a few. Gail is currently a senior mathematics advisor for Texas Instruments. So Gail, we're excited to have you here.
Thanks, Mike. I'm glad to be here.
And Tom is also a senior mathematics advisor for Texas Instruments and is professor and former chair of the math department of Oregon State University. He served on the editorial panels for the Journal for Research, Mathematics Education, and the Mathematics Teacher Educator. He remains active in the College Board's Advanced Placement Calculus program and has previously served as the chair of the AP Calculus Test Development Committee. He's been recognized by the Mathematical Association of America with its Distinguished University Mathematics Teaching Award for the Pacific Northwest, and in 2008 he was inducted by the Oregon Council of Teachers of Mathematics in the Oregon Mathematics Education Hall of Fame. So Tom, it's great to have you with us as well.
Yes, it's great to be here with you and Gail, Mike.
And to get us started, Gail, would you mind talking through our agenda for tonight?
So thanks, Mike. So tonight we thought that we would talk about how we might look at data using some TI technology, both the 84 and the Nspire. And we're going to look at optimal locations for a food truck. And then we're going to revisit with an eye to the 84 and to some functionality, the CO2 levels, the hurricanes, and herd immunity. We're going to look at some new directions, the game of hog, and then we're going to turn it back to Mike, and he's going to tell you about the webinar drawing.
Thanks so much, Gail. Yeah, stick around to the end. One lucky winner is going to receive a T-Cubed International Conference virtual registration. So stick around for that. Tom, talk through our expected outcomes, please.
Sure. So we're hoping that folks participating in this webinar will be able to get some insight into how they can create useful visualizations on both the TI-Nspire and TI-84 Plus. Understand what activities using really large data sets might look like, and identify ways to manage data using either the TI-Nspire or the TI-84. And most importantly, identify ways in which they can use data-driven activities incorporated not in just a special class, but across all their math classrooms.
Tom, thanks so much. We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions that you have to Gail or Tom using the Q&A window on the right side of your screen. And we'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. All right, Tom, you want to get us started? Feel free to share your screen.
Okay.
So while Tom is getting ready to share his screen, a lot of the things that we do are involving real data, and we're excited about the opportunity for kids to engage with real data. So there's a lot of research out there that says that using real data is something important for kids. It can open doors for them. It can help them think more critically and learn to argue from evidence. And notice that one of the resources for that is the science standards, which is kind of an overlap that we sometimes run into when we're doing data. And one of the things that's really clear is that when kids have a choice in the ways they approach a problem and in the problems that they choose to do, they are much more motivated to do the mathematics and more engaged. Next slide, Tom. So next slide, please, Tom.
Okay. There we go.
All right. And as we go through these, please put any questions or comments or thoughts in the chat, and one of us will try and respond to make sure that we're keeping in touch with you guys. So I just was actually at an event tonight, a baseball game, and the people behind me were talking about hiring a food truck. And I was like, okay, well, that's just what we're going to talk about. So food trucks are a really kind of an in thing. And it's a place that a lot of people go to get food to eat. Next slide. And so we thought we would look, next slide, please, Tom. We thought we would look at possible food truck sites in Washington, D.C. So I don't know how many of you have been to Washington, D.C. So I actually used to live there, and so picked out some of the sites that are pretty popular attractions. And so we have 11 of those sites that are located around DC. And we have way out at the end, I don't know if you can see them or not, there's a P and an M, and those are commissary sites, which is commissary. I always say that wrong. Tom and Curtis laugh at me. A commissary sites, which is where they park the food trucks at night, or and where they sometimes even do the cooking instead of doing it right on the food truck. Depends upon the kind of food truck. So next slide, please, Tom. So what are the things that you think would be important to consider? I should have probably not had Tom go to this slide right away. To consider when you were locating where you were going to park your food truck. So you're going to go into this business and you're going to get a food truck, and you're going to figure out where to go in Washington, D.C. So we identified some variables that we thought might make sense. And so you can see them on the slide. And with a little bit of digging, you can find things like the average number of visitors and workers. You can find, using census data, median income. You have to scrape around in the web to come up with some of these things, but you can find most of this kind of information if you really look. And so these are the variables that we decided to use. Next slide, please, Tom. And the commissary is where you get your costs, not just thinking about the cost of food, but thinking about just setting up this enterprise that you're going to go into. And so you have to pay money to park your truck at a commissary. And so the two that we were looking at actually were $125 per week or $500 per month. And you have to drive back and forth to those commissaries, so you care about how far away they are. And you have to pay. You can't just park on streets, at least in Washington, D.C. There are lottery sites, there are metered sites, and in some of them, you just like at the zoo, you just pay a flat fee for being able to park your truck there. Next slide, please. So, oh, back up, Tom. Sorry. All right. So I want to ask right now, how would you think about putting all of these variables together? So think a minute and then type it in the chat. What would you do if you had all those variables that we just looked at? The visitors, the number of other food trucks, the number of workers in the area, the number of hotels in the area, and then these costs. What would you do in order to put all that data together to try to come up with the optimal location for your food truck? So think a minute, type it in the chat. So we have one really interesting answer because it never even occurred to me. And I should have thought about that as a matrix. I think we have to think about that, Tom. That's pretty cool. We got graphs, we got weighted values, the relative locations, Voronoi diagram. We actually thought about that. Spreadsheet, graph. Okay, great. So we're going to look at not just only these ideas that you put out there, but we're going to actually figure out how do we do the mathematics that gets us there. So next slide now, please, Tom. So at a very elementary, like an 8th grade level, the kids might just actually rank the best site as number 1 and the worst site as number 11. Like who had the most weekday visitors, they would be number 1. Who had the second most would be number 2. And so they would take all the variables and rank them like that. And so you can see, and then make a graph, which is what you guys suggested. So you can see there that Farragut, Union Square, DuPont Circle, Metro, those are kind of plausible looking pretty good if this is the technique you use. The graph below that, the blue and brown one, shows you what happens if you factor in the cost. And again, you see DuPont Circle and Farragut Square, as well as Metro Center and Union Station, kind of show up as logical places that if this were the strategy that you used. Can anybody think about anything that might be wrong with this strategy? Maybe not wrong, but a disadvantage for using a strategy just purely on ranking. Anybody think of anything? Pop it in the chat if you can. Sharon's on this. She's worried about the profits. So we didn't actually, this would be another place where you would go. You would think about the kind of food and how much you would sell it for. And so they're taking traffic into account. So we're taking foot traffic into account. Not looking at the culture, the other businesses in the area. So you're right. Those are things that would be important. So one of the things that just with peer ranking, one disadvantage of just ranking those data, even if you went and got some more data, is that you're ignoring the variability. So you're missing, so suppose, for instance, that a Union Station has 1,000 visitors a day. And the next one down is the mall, and it only has 400 visitors a day. You're not taking into account that big gap between the first and the second place if you just rank. So we thought about other ways to do this. So next slide, please, Tom. So another way is to have kids standardize the variables by taking a fraction of the best. So if you notice that in the workforce variable in the spreadsheet there's a 1. That means that this was the maximum number of people in the workforce, the workers and visitors that were at that site. And this was site number 9. So I think that's Union Station. So that was the maximum number of workers, visitors that came through that site. And so we divided everything by that number in workers and visitors. And so we get kind of a comparison for that. And so if you look at the dot plot down on the lower left, the circles that are highlighted all go to Farragut Square. That Farragut Square looks really good. And if you look at the costs in the one to the right in the plot, it's kind of in the middle of the road of the costs. A lot of them all had the lottery ones all had the same cost, okay? But Farragut Square is a lottery, and there's only a 40% chance that you would get a parking space through the lottery. So about a 40%. So that's kind of iffy. Means that like some months you would get a parking space and maybe some months you wouldn't. Next slide, please. Another way to do this is to standardize the variables by using z-scores. Now, you don't actually really have to be in statistics before you can understand what this is, but this is probably an Algebra 2 approach. I probably wouldn't do this with my 9th graders. And so basically what you do is you calculate the z-scores for all of the variables, and you do exactly the same thing. Look at a plot of the z-scores. So if the z-scores are positive, it means they're above average. If they're negative, it means they're below average or the mean. And you can see that Farragut Square is looking good, and so is DuPont Circle. Union Station's not quite as good. DuPont Circle scores pretty high, and it's got an advantage. It's pretty costly. It's more costly than the other ones, but it's not a lottery. It's metered. Next slide, please, Tom. And somebody in here, one of you guys mentioned that we could put all this together. And so one of the things that you can do is sum the z-scores. You could sum the ranks. You could sum the other fractions as well. So you could just sum the z-scores by just finding the total. Or some of you were like, I would want to go for a weighted z-score. And so here you notice that in that sum of weighted z-scores, the factor in the coefficient for the number of visitors and the number of foot traffic through the metro are much bigger than the hotels or the income and some of the other factors, and have to minus off the cost. And that's pretty arbitrary, whatever you would want to do. But it looks like you're going to have to make a choice between DuPont Circle, Farragut Square, or Union Station. And here, this is where this working with data is pretty open-ended. Kids have to just create an argument for the site that they would choose and why they would make that choice. So next slide, please, Tom. So one of the things that we try to do is when we get kids engaged in these kinds of scenarios and come up with some kind of a conclusion, we also try to figure out, are there ways that we might extend it? So here's a communicating, extending activity, several of them that you might have students engage in to try to bring some closure or make some connections to where they live and what this food truck data would look like there. Okay, thanks. Next slide, please, Tom. It's over to you, Tom.
Okay. So these principles that you're seeing on the screen now, these are ones that, as we've been working on modeling and data science activities, that's Gail and myself and Curtis Brown at TI. Gail realized that we had been using some principles, and it would be good to actually articulate those. And so this is, I'll give tribute to Gail on this. This is her articulation. I really like it a lot. These principles are, when you're looking at data, is to really start out with informal before diving into the formal mathematics. So take a look, what do you notice, what do you wonder, those kinds of questions. Just trying to get a sense for what the numbers are telling you. And part of that informal before formal is also, delaying some of those formal definitions. Let those get developed through these real contexts. Then you can kind of scaffold toward more automaticity and formalism. And then as depending on the level of your students, you can then get into some reasoning about actual sampling distributions, visual displays of data. And it's always best then to circle around and to think about very carefully, how would you communicate what you found? How would you connect it to other data questions you may have seen? How would you extend it? What are the next questions that are raised? In general, we look at data and try to analyze it because we're trying to answer some questions. And that analysis often raises new questions. And actually taking the time to articulate those is good.
Okay, so I'm going to just chime in here because this is Tom, can you play the little video?
Oh, sure.
Click it. Yeah. And so this is something that it was kind of an awesome thing. So I'm not sure, is this little video playing or not? It doesn't look like it's playing.
Let's see. Okay.
Yeah.
Okay.
There you go.
There we go.
Yeah. And so you can just click one of a quantitative or qualitative variable, and it will highlight all of those variables in every other screen. That's the power of the linking. And so now I can go and I can click off on Farragut Square, a DuPont Circle, and I can move over to Farragut Square, click on Farragut Square, and it will highlight in all the other pages that I have in this problem, it will highlight all of the information. These are the z-scores for Farragut square. This is a really cool thing that can help kids make sense of the data. Over to you again, Tom.
Okay. Let's see, are we still playing?
No, you can just click onto the next
there we
paragraph.
go.
Yeah,
All
there
right.
we go.
Okay, so now we're going to kind of shift over to another problem or question. And this is one we should mention that Gail and I have done at least a couple other modeling webinars. And this is a topic that we haven't looked at before. We're going to look at it in a little bit different slant this time and actually look especially at using the TI-84 on this. Climate change has certainly been in the news. And something related to climate change is levels of carbon dioxide and how they affect climate change. So folks have been looking at global CO2 emissions, and there's some interesting data that's available to that. Also, CO2, besides its effects on global warming, it has a direct relationship to our own health. While it's necessary for us to breathe, too high a concentrations of CO2 could be a real problem. So you can see some of the data here. This slide reminds me of the movie about Apollo 13 and the difficulty they had when the CO2 levels were rising in the space capsule, and they had to figure out a way to scrub that out because it was affecting their thinking. So let's do this routine of just kind of looking at the numbers. Here is a list of CO2 levels. These are gathered from the observatory at Mauna Loa in Hawaii. And the month here, the number of the month is what you would expect. Month 1 is January, month 2 is February, and so on. And these are the CO2 levels each month, the average CO2 level in 2018. So what do you notice about those numbers, and what do you wonder about? So you might have thought that was a rhetorical question, but I'm waiting to see if anybody has some thoughts. Well, it does look like they're so some people are commenting they seem remarkably consistent, though we do see some variation from month to month. What's kind of interesting to me is that they look like they're rising and then dropping and then rising again. They're all just a bit over 400. I'll tell you what, let's go ahead and take a look. What do you wonder? Somebody's asked, is there some kind of an annual cycle? Maybe we should look at another year. Maybe several other years. How's that? Okay, so these are every year. Well, the ... is, there's a lot of columns there we're not showing. But we looked at this data back to 2006. And if you look in any particular column, you kind of see this similar, it's rising and then it falls, and then starts to rise again. So there does seem to be some kind of a cycle there, but if you look across the years, what do you notice? So we're seeing these increases. Yeah, for example, if you picked a particular month and looked at it each year, it looks like it's kind of definitely a rise in these CO2 levels. Okay. And so looking at this data, to take a closer look at it, pretty much cries out for looking at a graph. And these screens here, I think the last time we did this webinar, we used the TI-Nspire quite a bit on this problem, but it certainly lends itself very nicely to using the TI-84. So you can see that that graph in the upper left really kind of captures both things I think that we notice. We're seeing this kind of a cycle through the year, but then for different years, we're seeing that whole cycle raising up. So we're seeing two kinds of patterns here. The yearly average looks like it's rising, and in any single year, there's a kind of a cycle. The upper right, we have these box and whiskers for different years. And these two graphs are certainly ones that you could do with middle school students. As you start to work with students who maybe have a little bit more advanced mathematics background in terms of trigonometric functions, looking at regression, we could look at things like curve fitting. So in the lower left there, you see for a couple of years, the fitting a trigonometric or sinusoidal model to the years. What's something that kind of struck me when we first looked at this data was, I expected the period for the data to be basically 12 months, but that wasn't really taking into account that simultaneously there's this rise that's going on. And in the lower right, you could see a model that's actually incorporating both. And we can see this kind of a sinusoidal on a slant. That's a real technical term I use there. So, okay. And feel free to jump in, Gail, if you think I neglected. Here are some screens, actually from the Nspire. And certainly the Nspire is very nice. You do have the list editor on the 84. The spreadsheet functionality on Nspire really lends itself to looking at this data there. A question that might come up is, did the pandemic have some effect on the CO2 level? Because there was lower usage possibly of industries that would have generated the CO2. But it looks like when we looked at this, if there was any effect, it was very, very temporal. It was just very temporary and not much. And most recently, Gail gathered some more data. So one of the questions we want to look at is what would happen if we looked further back? And so she's gathered data all the way back to 1958. And this is fascinating to me. If you look at that graph in the lower left, you're plotting from 1958 to close to the present. The yearly averages, if you look at from 98 to 2022 in the upper left, it looks like they're going up kind of linearly. But if you look at an even larger interval, I don't know about you, but I'm kind of detecting a concave up look to that. It's starting to look somewhat exponential. And the graph on the right is actually showing a plot of the increase in the CO2 levels for each year. And Gail, before I move on, I really want to invite you to make any further comment, because I know you have really looked at this data quite a bit very recently.
So my only comment is this data is too much to put on the 84.
Okay, yeah.
Yeah, there's 300 plus rows, and the 84 has a limit.
Okay.
So you'd have to just use the yearly average instead of trying to go by the months. That's why it's all jiggered, is because it's got all the months in there as well.
Yeah. Right. Okay. And this is again looking at some curve fitting, and the ones from 98 through to the present really lends itself. If you're looking at the yearly average, it really lends itself to a linear fit. See that increase. But if you look at a much larger interval of years, notice we're looking at an exponential down there in the lower left. And if you're trying to forecast, the graph in the upper right kind of really shows the difference between that exponential model and that linear model if you were trying to predict what's going to happen in the future. The graph in the lower right, I don't think that's one that's generated by Nspire or 84. That's one we got from the literature. But you can see, we've got that kind of tight blue curve. That's actually off the actual data. As you move into the future, it's prognosticating. And so there's, you can see it starts to fan out. And that's taking into account the kind of uncertainty. You can think of that, the height of that spread there is kind of your confidence interval in terms of the prediction. Here's a question we really don't have an answer to, but we made us really curious here. If you actually look, they actually measure the uncertainty in their yearly CO2 levels. And you can see that between 74 and 75, there's this huge drop off in the uncertainty. So what in the world was going on there? Our best guess might be that their instrumentation possibly took a jump or big advance then, or their techniques. There was some breakthrough in there where they were able to come up with a much tighter confidence interval, if you will. The uncertainty in those mean monthly CO2 levels seems to be increasing, and well, why would that be the case? It's more recently. And then, of course, we always want to circle around and look at communicating and extending these ideas. When you see newspaper headlines, I love this type of question. Is take a newspaper headline and then actually tackle the question: is that really right? Can we support or refute what they're saying by looking at the data? Okay, Gail, I think that's going to turn this back over to you.
Okay, great. And so here's more news. So we try to work with data, that's real data, about things that are in the news. And so this stuff never happened 5 years ago. These were not words that we heard, and we didn't see this kind of mathematics except maybe in a statistics book. But now it's in the media everywhere. And so we need to think about, well, what does this make? How do we make sense out of this? And before I continue to go that way, I have to say that you guys are in the chat. You're actually offering some really good ideas about coal burning and the air conditioning and the change in the climate. And so that there's a lot of places where your students can go investigate what's actually happening with that CO2 level. So you're raising some really good points there. Okay, next slide, please, Tom. So we decided that what we would do is write an activity that would engage kids in figuring out how do we talk about some of these words? What do they mean? And so we're going to set up, and if this were, if I could identify you and could see your pictures, I would actually number 20 of you from 1 to 20, and I would have you show your picture or stand or whatever. And I'm going to assume that the disease is spreading. The 10% of my population is immune, either because they got a vaccination or because they already had the disease. I'm going to assume that you're contagious for only 1 day, and that when you have the disease, you, on average, give it to 2 other people. And so I have 2 questions. How long before the epidemic ends? And what proportion of the population will contact the disease before the epidemic ends? So we've got 1 to 20. You could use 1 to 30 or however many kids you have in your class. And 10% of them, so here 19 and 20 are going to sit down because they're immune. All the other 18 are standing. And so we generate a random number from 1 to 18 for a newly infected person who enters into the community. Okay, next slide, please, Tom. And so here's your class, and those are your 10% immune. Next slide. And poor little 15 gets the disease and sits down. And 15, next slide, please, transmit the disease to randomly, to other people, we generated the random numbers 8 and 18. And so 8 and 18 sit down, and they now affect 2 other people. So we randomly generate 2 more numbers, and we continue that process. If one of the numbers is somebody already sitting down, so if we randomly generated the number 15 again, then that wouldn't count as a new random number. So we continue that process till we've exhausted every time we hit the random numbers, we only do random numbers of people that are sitting down. That's the process that we're engaged in. And that process is going to identify for us what they call herd immunity. Next slide, please, Tom. So you can do this on the 84, exactly the same thing. So we set up a scatter plot, and we, by just generating random integers and storing them in L1 and L2, and then we generate our random integer. I did this from 1 to 100 this time. And the person who came in was 86. And that person is my newly infected person who's going to affect everybody else. Next slide, please, Tom.
Is it okay if I jump in here for just a little bit?
You go right ahead and jump in.
So I just want to emphasize to people that that graph on the right, that scatter plot there, this is just to be kind of a visual display aid. The actual coordinates of those little squares are not meaningful, and these are not proximal locations of the people to each other. It's just say, hey, here's 100 people, and we're going to start lighting these folks up with different colors to represent whether they're contagious, whether they're immune, and whether or not they've gotten over the disease. Okay? All right.
Thanks for doing that, Tom. Okay, so we've got our 86. That person, 86, belonged to the ordered pair 1528. So that ordered pair got highlighted, and that they generate more newly infected people. So we continue this process. Next slide. And we finally end up with 16 days from the start of the spread, there were no more newly infected people. So if you counted the little gray dots, only 30 of the original 100 were uninfected. So that herd immunity threshold is the percent of the population that was infected before the disease died out. So 70% of the population. So the herd immunity threshold would be 70%. Okay, next slide. And by the way, I was talking to Mike about this, Mike Houston, and it's really the ideas that are used in making the 84 generate those things are really cool. Just being able to arrow up and highlight and then click enter, and you get a new the line just pastes itself below. The 84 is very nice to do this with. And then there's a program that Tom wrote that you can enter all the numbers that you want. Okay, so you can enter the number that were originally infected. You can enter your total number who are susceptible. You can change your transmission rate. So we had a transmission rate of 2. You could change it down to 1.2, which was like what we were maybe with the COVID. You could enter the days contagious. So you can enter all of these different things and just run the program by just clicking enter, and you will eventually end up with a herd immunity threshold, which allows students to explore all sorts of different conjectures about what would happen if the transmission rate got higher or lower, how does the number of days contagious change what's going on. So it allows kids to just explore lots of different things. Next slide, please, Tom. And because I come from a statistics background, basically, whenever you collect data like that off of the simulation, you want to actually collect all your students' data. So you would like to just have them put it on a Google Sheet, or use, if you have Navigator, not Navigator. Yeah, you have Navigator, right? You could actually get this on, have them enter the data and send it to you, and whatever, you could even do it on a Blackboard. or your overhead, just to get some kind of a distribution here where all I'm really caring about for, 8th and 9th graders is it typically looks like the herd immunity threshold is going to be somewhere in between, and you'd have to use your little arrow to go around there, but somewhere between 65 and 80%, or 80, yeah, 84% maybe. And so you can, if you're teaching statistics, you can actually push it farther and do confidence intervals and that kind of stuff, but you don't really have to do that. And it looks like the mean number of days is going to be somewhere around 14 days before the disease would stop spreading. Next slide, please. So here's a switch back to the Nspire, just because it's kind of blows your mind. You really can't do 1,000 people in your community on the 84. It's just way too slow. But you can do, I'd probably do 200 maybe max with your students. And that's the picture that it looks there with 1,000. And the other thing, somebody mentioned logistics curves, and you can set this up so that all of the data are collected in tables. And you see those very nice little graphs there. They make some really nice conversations to have with your Algebra 2 kids about, is that really a logistics curve? What's the connection? What's the point of intersection mean? Notice that the gray one is the susceptible over time. The pink one is the recovered over the time. And the black one, the one that looks like almost like a symmetric mound-shaped distribution, is the number of infected over time, which you can see rises, which is what we care about in terms of hospitalization and hospital facilities. It rises in somewhere in 20 days for the picture that I'm looking here, is when you're going to get the peak number of infections, and then they start falling off. So there's lots of things you can do that connect to your math classes with these kind of data. Next slide, please.
And I'll just jump in real quickly here and say there's some really nice calculus conversations one could have here too. So, okay.
Yes, points of inflections, etc. And once you have either of the programs, there's a program for the Nspire as well, you can actually play around with a really important question. What percent do I need to have vaccinated before herd immunity threshold will come in? And this is running the simulations with a 10% vaccinated, a 50% vaccinated, and an 85% vaccinated. And you might notice this is a place where we would play with Tom's What Do You Notice? What Do You Wonder? The one in the top left is the length of time before the disease dies out at those different percents of immune. And does anybody notice anything that they want to point out in the chat? And somebody did, Todd did say this is the SIR, and that's a susceptible infected recovery modeling opportunity, and that's exactly right. Anybody notice anything they want to comment on in that length of time? I mean, this is a perfect place to talk about different kinds of graphs when you're looking at data. So you've got this little graph that's got very little variability. The 10% is very little variability. It's all nicely mound shaped. The 50% is all spread out. That's kind of interesting. That kind of blew my mind. And the 85% is skewed. Sometimes it takes a long time before the disease dies out, but most of the time it's over within 5 or 6 days, typically less than 15, which is way less than what's going on with the other 2%. The one in the bottom left is your herd immunity thresholds for those different percent immunes or vaccinated. And you can see again that there's something interesting at the 50%. And I could ask if anybody has a thought about what that might be. But I'll just point out that if you have a 50% of your population is vaccinated and somebody new infected walks into the room, they have a 50% chance of running into someone who's already been vaccinated, and then it dies out. And so that's why that little blurb down there right at the 50% for your herd immunity threshold, the little orange one on the far left, that's why that just kind of like sitting there. But then on the other hand, it goes way up. And again, you can see the idea that the 85% vaccinated is going to give you pretty good herd immunity threshold. Your herd immunity threshold is going to, in the next one at the next right, is going to protect 99% of those that have not yet been vaccinated. And that's a pretty big thing. And somebody asked for the link, and Mike put in the chat that we'll share the links. I will just point out that all of these activities so far are written up under either the 84 or the Math Inspired, and the resources and the TNS files and the 84 programs are available on the TI website. Next slide, please, Tom. And this slide, I just, because I was often had trouble trying to help my students understand why we cared about logarithms. Every time I see a graph that's got logarithms in it, I kind of get excited. And so this is a graph of about, it comes from what's going on in this graph. And we're just interested in looking at that. And it's the people infected by each sick person. That's your number, how you're contagious you are, or the transmission rate. And then the vertical axis is the fatality rate. So that's, and it's in a logarithmic scale. So I'm not teaching this semester, but I would actually take this to my kids and say, what would that look like if it weren't logarithmic? Why is log scale a good way to do this? What would happen if it weren't? And it's kind of interesting just to notice that measles infects, it's very infectious, but it doesn't have a high fatality rate. On the other hand, bird flu and Ebola have a huge, they don't infect very many people, but they have a huge fatality rate. And Tom offered, and I think he's probably right, that the reason they don't infect very many people is they die right off the bat. They're not around long enough to affect very many people when they get some of those diseases. Okay, next slide, please, Tom. And this is the communicating and connecting extension. You might just try this with other things. Okay, on to the next one, Tom.
Okay. So this is floods in the news. This has to do with optimizing resources. So it kind of comes circling around to the food truck problem. Was really about kind of optimizing your choice of location. This is kind of related to that. Floods have been in the news quite a bit lately, and this gave us reason to maybe look at some data from a flood that occurred a while back from a hurricane. This was Hurricane Sandy. And the question, or the real question that came up, Hurricane Sandy, was they anticipated this big storm surge, but they had, so they were going to have power outages, and they were also had people who were vulnerable, like seniors in assisted living. And the question was, if we have a limited number of generators and evacuation buses, where should we locate those resources optimally? So, so the question was, which of the tracks on Staten Island was going to get hit hard? And they said, well, where should we position these to have the best impact? And it's a lot of data. These are the different census tracts on Staten Island. Gives the number of blocks in that tract, its elevation above sea level, the percentage of people in that tract that are greater than or equal to 65 years old, and actually the raw number, and also the number greater than or equal to 75. total population and track, and we could also get into demographic data, for example, ethnic data. So a big spreadsheet. How do we make sense out of it? Where should we place these generators and our buses? Love this quote from Subramanian. He said, "Where should we put them? You just had to guess. Can you imagine what a mess that would be?" This was an occasion. This is one where our best work on this, we really did need to use Nspire and take advantage of it. The data was a little bit too big and unwieldy for using the TI-84. And Gail, you might want to say something about your use of coloring on the spreadsheet here.
Yeah, so one of the kind of very 8th, 9th grade approaches here is they could just use color. And we'll show you in a minute how to color the cells or the rows if you don't know that. But they could just say, okay, let me identify a storm surge and say, maybe the storm surge is going to go 18 feet. So I'm going to look for places that are a track that is lower than 18 feet. And I'm going to color all the tracks that are lower than 18 feet. They're above sea level. They're going to get colored orange. And then I'm going to identify a threshold of population over 65, and they're going to get colored blue. And the intersection of those two are where I'm going to go for placing my generators or sending my buses. Okay, I'm good.
All right. Okay. And kind of a next step here, and I think you see these maps here. These were actually done on the Nspire. We actually attached some of the that spreadsheet of data. These tracks in these maps are actually conditionally colored. And so the sliders control some of these key variables, and the color of the track tells us whether or not it is at a particular threshold. I think I'm going to actually illustrate this one on Nspire. So I'm going to switch over to Nspire. And this is our Nspire file for this particular problem. It's called Optimizing Resources Using Census Data. Let me move over to page 1.3. This is just a big spreadsheet with exactly the kind of data that Gail was talking about. You can see that we've got a color on the cell there. And then we've made this interactive Staten Island map. And the way this map works is the tracks on the map will be colored green if their elevation is below a certain maximum elevation. And you get to set what that maximum is. So you control what's the threshold for being colored green. If the number of seniors greater than or equal to 75 is above a certain minimum, it'll get colored orange. And if it satisfies both of those criteria, it'll be colored magenta. And if it satisfies neither, it's gray. All right, so let's take a look at what that interactive map looks like. And you'll notice here, I've got the minimum number of seniors greater than or equal to 75 set at 0. That's why so many of those tracks are orange, is that that's a pretty easy threshold to satisfy. But if I increase that, you can see that we get less of the orange tracks. And the green tracks here, elevation is under 30 feet, but I could lower that elevation threshold. And the ones that are colored magenta are satisfying both. So it's a nice way to play around with those two kind of key variables. And as I said, the magenta ones are the ones that are meeting both criteria. And so that's that intersection that Gail was talking about. In the interest of time, let me go back and our PowerPoint, of course, communicating, extending. You know, the whole notion of a 100-year flood is really changing these days. So they may need to revise what that means. Let's see.
Okay, so just click this one again. So We thought we'd show you how to color the rows because we discovered that people didn't know how to do that. So when you highlight, you can't actually be in the cell. You have to just have the cell highlighted. And then you go to File and Edit and Fill Color. And you just choose the color that you want to fill. I think I'm going to fill it with brown, so I arrowed over, or orange actually. Yep. And so now I filled the cell. If I want to fill the whole row, I go to Actions to Select and select the row or the column, whichever. And now once I've selected that, I repeat that going back to my documents, my edit, my color, fill color. And this time I think I'm just going to do text. And so I'm going to fill the text color with brown. And that's how you can see the point of intersection. So that's how you put the colors in there. Okay, so we're just about out of time. So Tom, can you go to the next slide? I think we're going to have to skip I'm going to do Hog in 1 minute. So we've done this before. If you haven't played Hog, you have 1 to 7 dice, say, and you can throw any number and you get the score that shows up, unless you have a 6 and then you get 0. And so the question is, how do I keep, what's the optimum number of dice I should throw? And so you start with the kids and they play this game and they like it and they're very curious about what happens. Next slide, please, Tom. And after they played the game a few times, you actually want to go to the technology. And again, this is the 84 is just really nice to do that. You generate random integers and you store them and you collect them all. And we're not going to continue to do that, but they can simulate this and see what happens. And I'm not going to tell the answer. And go to the next slide, please, Tom. And there's that was 2 dice. So next one. And there's an awesome little video that you might want to explore that brings the math out. That would be really cool. And next slide. And Michael, oh, we're not going to do that. Keep going all through these because we're out of time. This is coming attractions. So we're not going to talk about those because we just don't have time. There's where you can find all these activities, modeling with TI technology. And I want to take 1 minute or 30 seconds at least for the next slide, because we were just talking about how hard it is for teachers to figure out how to put these activities in their classrooms. So some of our suggestions are you could use them as an alternate assessment. So at the end of a chapter, instead of giving them the book assessment, take one of these activities that might have some of the ideas that relate to some of the things that you've been talking about in the chapter. Won't be exhaustive, but it'd be a great way to assess what kids really took away from that activity. As give them as projects. I used to do this. My kids had a project at least once every quarter, sometimes once every chapter. And they handed them in and they got just like a test. They got assessed and graded on that. You can incorporate them into units. Somebody mentioned that the SRI model in calculus, that actually is founded in differential equations, so it's a great place to go. Or you can create a semester course that would work as well. But I just wanted to throw all that out because don't say, I can't use these things. And the other thing is, don't be afraid of letting the kids run with it. They have a great time if it's something they're interested in, and they will support you. You don't have to support them so much. Okay, over to Mike.
All yours, Mike.
Thanks so much, Gail and Tom. So as promised, we're giving away to one lucky winner a T-Cubed International Conference registration for our virtual conference coming up in July. And tonight's lucky winner is Karen Shimley. So Karen, congratulations. We'll be in touch over the next probably a couple weeks here over email to give you a little more information about that. But we hope to see you as well as everyone else at the T-Cubed International Conference, which again is virtual this year. One thing I did want to mention, we do have 2 more webinars coming up this spring. And so if you hop over to our website, education.ti.com, where Gail was just showing where you can get some of those activities that were used tonight, you can also hop under the professional development tab and look under webinars. If you peek under there, not only there are the on-demand webinars, but there's also the live upcoming webinars. And we have 2 more on Tuesday nights. Next Tuesday, we'll be doing one that involves leveraging CAS in the algebra classroom. And then late April, we're going to be doing a SAT prep with Tom Reardon. So feel free to register for those. Again, they're free. We'd love to see you. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed was a link for the documents that were used tonight, and if for any reason these links aren't working for you, just hang tight. You should automatically be getting an email within a couple days, and that will contain a link to the recording so you can watch at your own pace, a link to the certificate, and the documents as well. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. So huge thanks to Gail and Tom for everything they put together today. We really appreciate it. Thanks so much, Gail and Tom.
Thank you.
Thank you, guys.
Thank you, everybody.
Thanks, Mike, and thank you guys for being with us.
And we hope to see everyone back online next week for CAS. Have a great night.